This lecture segment ties together prior discussions to give a complete picture of the memory space for a standard running program or process. A clear understanding of the process space is critical to writing reliable C and for deeper study of operating systems. As prerequisite material, please review, if necessary, the concepts of the runtime stack, runtime heap, string table, global data, static local data, MMU and virtual address spaces, and the concept of a memory segment. A 32-bit architecture with 4-byte addresses and pointers permits 4 gigabytes of addressable memory in a program, and a 64-bit architecture permits as many as 16 quintillion bytes. Either way, that's a lot of bytes, and different areas of that huge space are used for different purposes. In prior lectures, we've discussed many of the different areas of memory that make up a running program. Let's review those and add a few more terms and concepts. I'll sort of fill in a diagram of a process memory space in abstract form as we go. So first up we have program code in machine language form, which takes up part of the running memory in what is usually called the text section or text segment of memory. So we'll label that here. Function pointers, for instance, contain addresses into the text segment. Now, you'd expect this to be called the code segment since it contains code, not text. But the name comes from the outdated term program text, and we're stuck with it. In many operating systems, the text segment is further divided into an area that's filled with machine language upon program startup, and another that's reserved for loading dynamic libraries as the program runs. Such libraries are loaded into memory only when the code that they contain is actually called. So let's add those here. Even though they're only loaded when used, still space must be reserved for them. That seems a waste of space, perhaps, but we'll see later in the lecture that clever use of the MMU makes it very efficient. Now, the next item is the data segment, and this is the area of memory that holds global data, as opposed to the runtime stack, which holds local data and parameters and so forth. Of course, a well-written program has little, if any, global data, but in this context the term applies to any data of which there is only one copy shared by all the function calls in the program. Data not local to any one function call. Thus, the string table and static local variables also fall in the data segment. Now, here's the first question for you. Wait a minute. Aren't static locals still local to one function? Why do they go in the data segment? And ditto for string constants. Any one string constant appears in just one function, right? So think about that. Coming back from a pause, this is really kind of a review question. Remember that static locals are local to a function, but what I said above was that the data segment contains data not local to any one function call, data that doesn't belong in a runtime stack frame, in other words. Multiple calls of a function share the same one static local variable. Static locals are thus global data in disguise. They don't go on the RTS. Review the earlier lecture, by the way, on global data if needed. And while a string constant may be created in one function, or may be passed around to other functions by reference, the sequence of characters comprising the constant must thus persist outside of any one function call. So string constants are also, in effect, global variables in disguise. Like the text segment, the data segment is usually divided into 2 areas. The main data segment holds global data that is initialized on program startup, such as the string table, and variables that are initialized in their declarations. And a reserved area of the data segment, usually called the BSS segment, holds global data that is uninitialized on program startup. Now, why separate initialized global data from uninitialized? Because global data is not initialized by running a bunch of assignment statements before starting the main program. It makes more sense and is much faster to store a binary image of the initial global data and copy it directly into the data segment as part of loading the program in the first place. So a compiled executable does not include only code, but also a binary copy of the content of the data segment, not the BSS segment, which binary copy is loaded into memory along with the code on program start. So to a rough approximation, we can think of our executable file here as comprising code, of course, which would get copied into the text segment, and global data, thus with that being copied to the data segment and the code, of course, being copied into the text segment. But uninitialized global data doesn't need to be stored in this way. The executable only needs to hold a count of the bytes, the number of bytes for such data, so we know how big to make the BSS segment. The term BSS originated in the 1950s with assembler code and stands rather awkwardly for block started by symbol. This suggests an area of memory that is brought into existence merely by declaring a global variable or a symbol in 1950s assembler speak. So it makes sense to group all the initialized global data together so it can be initialized in one big binary copy from the executable, while uninitialized global data goes in a separate area. The runtime heap and the RTS are yet two other areas of memory. We've talked a good bit about these already, but note that they differ from the text and data segments in one important way. They may grow during program execution. The runtime heap starts at some initial size and can generally be expanded up to a point if more dynamic memory is needed. The RTS also starts off small, with just the frame for main, but it may grow quite large as calls occur, especially if it, for instance, has recursive calls. So in our abstract diagram, let's show the RTS at the end of memory and growing upward as it did in our earlier RTS lecture. Now the space between these two will be room to grow, though there's a more complex story behind this that we'll cover a little bit later. First, though, let's take a closer look at initialization of BSS data. In almost all modern operating systems, the BSS is automatically initialized to all 0 bytes. This is not so much a part of loading the program as it is a side effect of operating system policy. The operating system itself sets the entire area of memory given to a new program to all zeros, so you get initial data of 0 for free if you don't otherwise initialize the memory in your program with data or with code. This applies to any area of memory, including the RTS and runtime heap, as well as the BSS segment. And so here's question 2. Why is it necessary for the operating system to do this? It's not being done to save you from uninitialized data. This is C, after all, and initialization is your problem. There's an important security issue involved. Imagine the ongoing history of programs starting, running, ending, new programs starting, etc. In that context, what would be wrong with leaving memory that is given to a new program uninitialized? Coming back from a pause, the uninitialized data would be data either from the operating system kernel itself or from some earlier running program that had occupied that area of memory. And this invites a clever user to simply read the uninitialized content of the memory with which his program was started and obtain valuable information, like social security numbers or passwords or account numbers, from the garbage left in memory by earlier programs. This is not just an obscure possibility. The college I attended in the late 70s had an HP 3000 time-sharing computer, and its relatively primitive operating system did not zero out memory between programs. So clever students could dump the initial garbage in their program's memory space and get other people's username and password combinations from it. It was quite a security hole. So, wait a minute here. I've been prating on throughout the course about the dangers of uninitialized variables. unlucky bugs, and so forth. And now I'm telling you that you can be sure that your program's memory will contain zeros by default in all modern operating systems? Does that mean there really isn't a possibility of garbage data? Well, let's think about that more carefully with question 3 here. This doesn't mean, in fact, that you won't hit uninitialized variables containing garbage. How could you get non-zero garbage data despite this operating system policy, say in a local variable? Or how about in an allocated block from the runtime heap? Describe exactly the scenario that would cause uninitialized data, even given the operating system policy of zeroing out memory initially, and describe where the non-zero garbage data would come from. And coming back from a pause, well, if you make a function call A, let's say, and return from it, and then make a new function call B, the stack frame area for B overlaps the old frame for A, and will contain A's leftover garbage. We went over this in some length in earlier lectures. And if you allocate a block, fill it, and then free it, a later allocation may get that same area of memory, complete with the old data that you put into it. So, uninitialized variables are still a problem, but the important and somewhat interesting point is that any garbage data you see in a variable is your data from earlier uses by your program of the same area of memory. It never comes from some other program, at least not in any operating system with half a brain.